Hi, this is Sleeper. Welcome back to my channel. We are continuing with the read through of Web Security Academy with Business Logic Vulnerabilities. In this section, we'll introduce the concept of business logic vulnerabilities and explain how they can arise due to flawed assumptions about user behavior. We'll discuss the potential impact of logic flaws and teach you how they can be exploited. You can also practice what you've learned using our interactive labs, which are based on real bugs that we've encountered in the wild. Finally, we'll provide some general best practices to help you prevent these kinds of logic flaws arising in your own applications. What are business logic vulnerabilities? Business logic vulnerabilities are flaws in the design and implementation of an application that allow an attacker to elicit unintended behavior. This potentially enables attackers to manipulate legitimate functionality to achieve a malicious goal. These flaws are generally the result of failing to anticipate unusual application states that may occur, and consequently, failing to handle them safely. Note: in this context, the term business logic simply refers to the set of rules that define how the application operates. As these rules aren't always directly related to a business, the associated vulnerabilities are also known as application logic vulnerabilities or simply logic flaws. Logic flaws are often invisible to people who aren't explicitly looking for them, as they typically won't be exposed by normal use of the application. However, an attacker may be able to exploit behavioral quirks by interacting with the application in ways that developers never intended. One of the main purposes of business logic is to enforce the rules and constraints that were defined when designing the application or functionality. Broadly speaking, the business rules dictate how the application should react when a given scenario occurs. This includes preventing users from doing things that will have a negative impact on the business or that simply don't make sense. Flaws in the logic can allow attackers to circumvent these rules. For example, they might be able to complete a transaction without going through the intended purchase workflow. In other cases, broken or non-existent validation of user-supplied data might allow users to make arbitrary changes to transaction-critical values or submit nonsensical input. By passing unexpected values into server-side logic, an attacker can potentially induce the application to do something that it isn't supposed to do. Logic-based vulnerabilities can be extremely diverse and are often unique to the application and its specific functionality. Identifying them often requires a certain amount of human knowledge, such as an understanding of the business domain or what goals an attacker might have in a given context. This makes them difficult to detect using automated vulnerability scanners. As a result, logic flaws are a great target for bug bounty hunters and manual testers in general. How do business logic vulnerabilities arise? Business logic vulnerabilities often arise because the design and development teams make flawed assumptions about how users will interact with the application. These bad assumptions can lead to inadequate validation of user input. For example, if the developers assume that users will pass data exclusively via a web browser, the application may rely entirely on weak client-side controls to validate input. These are easily bypassed by an attacker using an intercepting proxy. Ultimately, this means that when an attacker deviates from the expected user behavior, the application fails to take appropriate steps to prevent this and subsequently fails to handle the situation safely. Logic flaws are particularly common in overly complicated systems that even the development team themselves do not fully understand. To avoid logic flaws, developers need to understand the application as a whole. This includes being aware of how different functions can be combined in unexpected ways. Developers working on large code bases may not have an intimate understanding of how all areas of the application work. Someone working on one component could make flawed assumptions about how another component works, and as a result, inadvertently introduce serious logic flaws. If the developers do not explicitly document any assumptions that are being made, it is easy for these kinds of vulnerabilities to creep into an application. What is the impact of business logic vulnerabilities? The impact of business logic vulnerabilities can, at times, be fairly trivial. It is a broad category and the impact is highly variable. However, any unintended behavior can potentially lead to high severity attacks if an attacker is able to manipulate the application in the right way. For this reason, quirky logic should ideally be fixed even if you can't work out how to exploit it yourself. There's always a risk that someone else will be able to. Fundamentally, the impact of any logic flaw depends on what functionality it is related to. If the flaw is in the authentication mechanism, for example, this could have a serious impact on your overall security. Attackers could potentially exploit this for privilege escalation or to bypass authentication entirely, gaining access to sensitive data and functionality. This also exposes an increased attack surface for other exploits. Flawed logic in financial transactions can obviously lead to massive losses for the business through stolen funds, fraud, and so on. You should also note that even though logic flaws may not allow an attacker to benefit directly, they could still allow a malicious party to damage the business in some way. What are some examples of business logic vulnerabilities? The best way to understand business logic vulnerabilities is to look at real-world cases and learn from the mistakes that were made. We've provided some concrete examples of a variety of common logic flaws, as well as some deliberately vulnerable websites so that you can practice exploiting these vulnerabilities yourself. So we have the examples of business logic vulnerabilities. Business logic vulnerabilities are relatively specific to the context in which they occur. However, although individual instances of logic flaws differ hugely, they can share many common themes. In particular, they can be loosely grouped based on the initial mistakes that introduced the vulnerability in the first place. In this section, we'll look at examples of some typical mistakes that design and development teams make and show you how they can directly lead to business logic flaws. Whether you're developing your own applications or auditing existing ones, you can take the lessons learned from these examples and apply the same critical thinking to other applications that you encounter. Examples of logic flaws include excessive trust in client-side controls, failing to handle unconventional input, making flawed assumptions about user behavior, domain-specific flaws, and providing an encryption oracle. Excessive trust in client-side controls. A fundamentally flawed assumption is that users will only interact with the application via the provided web interface. This is especially dangerous because it leads to the further assumption that client-side validation will prevent users from supplying malicious input. However, an attacker can simply use tools such as burp proxy to tamper with the data after it has been sent by the browser, but before it is passed into the server-side logic. This effectively renders the client-side controls useless. Accepting data at face value without performing proper integrity checks and server-side validation can allow an attacker to do all kinds of damage with relatively minimal effort. Exactly what they are able to do to achieve is dependent on the functionality and what it is doing with the controllable data. In the right context, this kind of flaw can have devastating consequences for both business-related functionality and the security of the website itself. Failing to handle unconventional input. One aim of the application logic is to restrict user input to values that adhere to the business rules. For example, the application may be designed to accept arbitrary values of a certain data type, but the logic determines whether or not this value is acceptable from the perspective of the business. Many applications incorporate numeric limits into their logic. This might include limits designed to manage inventory, apply budgetary restrictions, trigger phases of the supply chain, and so on. Let's take the simple example of an online shop. When ordering products, users typically specify the quantity that they want to order. Although any integer is theoretically a valid input, the business logic might prevent users from ordering more units than are currently in stock, for example. To implement rules like this, developers need to anticipate all possible scenarios and incorporate ways to handle them into the application logic. In other words, they need to tell the application whether it should allow a given input and how it should react based on various conditions. If there is no explicit logic for handling a given case, this can lead to unexpected and potentially exploitable behavior. For example, a numeric data type might accept negative values. Depending on the related functionality, it may not make sense for the business logic to allow this. However, if the application doesn't perform adequate server-side validation and reject this input, an attacker may be able to pass in a negative value and induce unwanted behavior. Consider a funds transfer between two banks. This functionality will almost certainly check whether the sender has sufficient funds before completing the transfer. But if the logic doesn't sufficiently prevent users from supplying a negative value in the amount parameter, this could be exploited by an attacker to both bypass the balance check and transfer funds in the wrong direction. If the attacker sent negative $1,000 to the victim's account, this might result in them receiving $1,000 from the victim instead. The logic would always evaluate that negative $1,000 is less than the current balance and improve the transfer. Simple logic flaws like this can be devastating if they occur in the right functionality. They are also easy to miss during both development and testing, especially given that such inputs may be blocked by client-side controls on the web interface. When auditing an application, you should use tools such as burp proxy and repeater to try submitting unconventional values. In particular, try input in ranges that legitimate users are unlikely to ever enter. This includes exceptionally high or exceptionally low numeric inputs and abnormally long strings for text-based fields. You can even try unexpected data types. By observing the application's response, you should try and answer the following questions. Are there any limits that are imposed on the data? What happens when you reach those limits? Is any transformation or normalization being performed on your input? This may expose weak input validation that allows you to manipulate the application in unusual ways. Keep in mind that if you find one form on the target website that fails to safely handle unconventional input, it's likely that other forms will have the same issues. Making flawed assumptions about user behavior. One of the most common root causes of logic vulnerabilities is making flawed assumptions about user behavior. This can lead to a wide range of issues where developers have not considered potentially dangerous scenarios that violate these assumptions. In this section, we'll provide some cautionary examples of common assumptions that should be avoided and demonstrate how they can lead to dangerous logic flaws. Trusted users won't always remain trustworthy. Applications may appear to be secure because they implement seemingly robust measures to enforce the business rules. Unfortunately, some applications make the mistake of assuming that having passed these strict controls initially, the user and their data can be trusted indefinitely. This can result in relatively lax enforcement of the same controls from that point on. If business rules and security measures are not applied consistently throughout the application, this can lead to potentially dangerous loopholes that may be exploited by an attacker. Users won't always supply mandatory input. One misconception is that users will always supply values for mandatory input fields. Browsers may prevent ordinary users from submitting a form without a required input, but as we know, attackers can tamper with parameters in transit. This even extends to removing parameters entirely. This is a particular issue in cases where multiple functions are implemented within the same server-side script. In this case, the presence or absence of a particular parameter may determine which code is executed. Removing parameter values may allow an attacker to access code paths that are supposed to be out of reach. When probing for logic flaws, you should try removing each parameter in turn and observing what effect this has on the response. You should make sure to only remove one parameter at a time to ensure all relevant code paths are reached. Try deleting the name of the parameter as well as the value. The server will typically handle both cases differently. Follow multi-stage processes through to completion. Sometimes tampering with a parameter in one step will have an effect on another step further along in the workflow. This applies to both URL and post parameters, but don't forget to check the cookies too. This simple process can reveal some bizarre application behavior that may be exploitable. Users won't always follow the intended sequence. Many transactions rely on predefined workflows consisting of a sequence of steps. The web interface will typically guide users through this process, taking them to the next step of the workflow each time they complete the current one. However, attackers won't necessarily adhere to this intended sequence. Failing to account for this possibility can lead to dangerous flaws that may be relatively simple to exploit. For example, many websites that implement two-factor authentication, 2FA, require users to log in on one page before entering a verification code on a separate page. Assuming that users will always follow this process through to completion and, as a result, not verifying that they do, may allow attackers to bypass the 2FA step entirely. Making assumptions about the sequence of events can lead to a wide range of issues even within the same workflow or functionality. Using tools like burp proxy and repeater, once an attacker has seen a request, they can replay it at will and use forced browsing to perform any interactions with the server in any order they want. This allows them to complete different actions while the application is in an unexpected state. To identify these kinds of flaws, you should use forced browsing to submit requests in an unintended sequence. For example, you might skip certain steps, access a single step more than once, return to earlier steps, and so on. Take note of how different steps are accessed. Although you often just submit a GET or POST request to a specific URL, sometimes you can access steps by submitting different sets of parameters to the same URL. As with all logic flaws, try to identify what assumptions the developers have made and where the attack surface lies. You can then look for ways of violating these assumptions. Note that this kind of testing will often cause exceptions because expected variables have null or uninitialized values. Arriving at a location in a partly defined or inconsistent state is also likely to cause the application to complain. In this case, be sure to pay close attention to any error messages or debug information that you encounter. These can be a valuable source of information disclosure, which can help you fine-tune your attack and understand key details about the back-end behavior. Domain-specific flaws. In many cases, you will encounter logic flaws that are specific to the business domain or the purpose of the site. The discounting functionality of online shops is a classic attack surface when hunting for logic flaws. This can be a potential goldmine for an attacker, with all kinds of basic logic flaws occurring in the way discounts are applied. For example, consider an online shop that offers a 10% discount on orders over 1,000. This could be vulnerable to abuse if the business logic fails to check whether the order was changed after the discount is applied. In this case, an attacker could simply add items to their cart until they've hit the $1,000 threshold, then remove the items they don't want before placing the order. They would then receive the discount on their order, even though it no longer satisfies the intended criteria. You should pay particular attention to any situation where prices or other sensitive values are adjusted based on criteria determined by user actions. Try to understand what algorithms the application uses to make these adjustments and at what point these adjustments are made. This often involves manipulating the application so that it is in a state where the applied adjustments do not correspond to the original criteria intended by the developers. To identify these vulnerabilities, you need to think carefully about what objectives an attacker might have and try to find different ways of achieving this using the provided functionality. This may require a certain level of domain-specific knowledge in order to understand what might be advantageous in a given context. To use a simple example, you need to understand social media to understand the benefits of forcing a large number of users to follow you. Without this knowledge of the domain, you may dismiss dangerous behavior because you simply aren't aware of its potential knock-on effects. Likewise, you may struggle to join the dots and notice how two functions can be combined in a harmful way. For simplicity, the examples used in this topic are specific to a domain that all users will already be familiar with, namely an online shop. However, whether you're bug bounty hunting, pen testing, or even just a developer trying to write more secure code, you may at some point encounter applications from less familiar domains. In this case, you should reach as much documentation as possible, and, where available, talk to subject matter experts from the domain to get their insight. This may sound like a lot of work, but the more obscure the domain is, the more likely other testers will have missed plenty of bugs. And lastly, providing an encryption oracle. Dangerous scenarios can occur when user-controllable input is encrypted and the resulting ciphertext is then made available to the user in some way. This kind of input is sometimes known as encryption oracle. An attacker can use this input to encrypt arbitrary data using the correct algorithm and asymmetric key. This becomes dangerous when there are other user-controllable inputs in the application that expect data encrypted with the same algorithm. In this case, an attacker could potentially use the encryption oracle to generate valid encrypted input and then pass it into other sensitive functions. The issue can be compounded if there is another user-controllable input on the site that provides the reverse function. This would enable the attacker to decrypt other data to identify the expected structure. This saves them some of the work involved in creating their malicious data, but it is not necessarily required to craft a successful exploit. The severity of an encryption oracle depends on what functionality also uses the same algorithm as the oracle. In conclusion, how to prevent business logic vulnerabilities. In short, the keys to prevent business logic vulnerabilities are two. Make sure developers and testers understand the domain that the application serves, and avoid making implicit assumptions about user behavior or the behavior of other parts of the application. You should identify what assumptions you have made about the server-side state and implement the necessary logic to verify that these assumptions are met. This includes making sure that the value of any input is sensible before proceeding. It is also important to make sure that both the developers and testers are able to fully understand these assumptions and how the application is supposed to react in different scenarios. This can help the team to spot logic flaws as early as possible. To facilitate this, the development team should adhere to the following best practices whenever possible. Maintain clear design documents and data flows for all transactions and workflows, noting any assumptions that are made at each stage. Write code as clearly as possible. If it's difficult to understand what is supposed to happen, it will be difficult to spot any logic flaws. Ideally, well-written code shouldn't need documentation to understand it. In unavoidably complex cases, Producing clear documentation is crucial to ensure that other developers and testers know what assumptions are being made and exactly what the expected behavior is. And note any references to other code that uses each component. Think about any side effects of these dependencies if a malicious party were to manipulate them in an unusual way. Due to the relatively unique nature of many logic flaws, it is easy to brush them off as a one-time mistake due to human error and move on. However, as we've demonstrated, these flaws are often the result of bad practices in the initial phases of building the application. Analyzing why a logic flaw existed in the first place and how it was missed by the team can help you spot weaknesses in your processes. By making minor adjustments, you can increase the likelihood that similar flaws will be cut off at the source or caught earlier in the development process. Once again, my name is Sleeper, and that's a wrap. Until next time.